Welcome to The Explainer. Today, we're taking a deep dive literally into the hidden anatomy of the roads you drive on every single day. I'm incredibly excited to share this with you because, honestly, the sheer amount of engineering buried right under our feet is just mind-blowing. We're going to look at the whole shebang, from the dirt right below your tires, all the way up to the digital self-healing smart roads of the near future. But hey, let's start with a totally universal frustration. You're driving along a perfectly paved road, just enjoying the smooth ride, and suddenly, bam! You hit a massive pothole. Or maybe you notice a sudden sinkhole forming right in the middle of a driveway. So why exactly does that happen? Well, it turns out the root cause almost never starts at the surface. The real culprit is usually hiding deep underground.
Here's our structural roadmap for today's explainer. We're going to build our knowledge from the ground up, starting with the anatomy of a pavement. Then we'll compare base versus subbase, tackle the drainage dilemma, look at flexible pavement systems, and finally, wrap up with future construction innovations.
Okay, let's dive into Section 1, Anatomy of a Pavement, or what I like to call the layer cake of infrastructure.
You see, professional contractors build roads from the bottom up, using 4 very distinct layers. It's kind of like a giant, incredibly heavy layer cake. It starts at the very bottom with the subgrade, which is really just the native soil that's been graded and compacted. Next up is the subbase layer. That's our first engineered layer of structural support. Above that sits the base layer, a tightly compacted platform. And finally, the surface layer. That's the asphalt or concrete that we actually see and drive on. Every single one of these layers has to be perfectly executed to support the weight of daily traffic.
I really want to highlight a crucial point from our engineering sources here. Without properly installed base and subbase layers, pavement systems can quickly fail. It's absolutely true. While that glossy surface layer gets all the glory, those unseen foundation layers, they are the true MVPs of our infrastructure. If the layers underneath fail, well, that beautiful surface above is doomed to crack and sink.
Moving right along to Section 2, Base versus Subbase, where we'll be distinguishing these hidden layers.
Now, what's really interesting here is how often the terms base and subbase get thrown around interchangeably by novices, but in the engineering world, they have totally distinct critical roles. The subbase is deeper, it's thicker, and it's made of larger, coarser particles. Its main job is load distribution, spreading the massive weight of vehicles across the soil, and handling drainage. The base layer, on the other hand, sits right under the surface. It's thinner, made of much finer crushed rock that compacts really tightly. This provides precise structural strength and a perfectly level platform. So they're teams, sure, but they do completely different jobs.
And when it comes to actually laying these materials down, there's a magic number you need to know: 70%. That is the minimum relative density recommended for subbase compaction. Why? Because compaction squeezes out the air pockets and physically locks those crushed particles together. If you don't hit that 70% density, the road is going to settle over time. And yep, those dreaded potholes are absolutely going to form.
Engineers actually select very specific types of crushed rock based on what a layer needs to do. For instance, for a base layer, they might use something called Class 2 road base. This contains fines, which are basically tiny particles and dust that act kind of like a glue, allowing for extremely tight compaction and serious structural support. But if drainage is the main priority, like in a subbase, they'll go with drain rock. Drain rock contains 0 fines. That means there are large empty spaces left between the rocks, which allows water to just move freely right through it.
That brings us to Section 3, the drainage dilemma, or as I like to call it, infrastructure's hidden enemy.
Make no mistake, water is the ultimate villain here. Trapped water is literally the #1 threat to a road. So, to fight this, engineers focus heavily on a concept called hydraulic conductivity. Now, the formal definition is the rate of discharge of water through a unit cross-sectional area of a soil medium under a unit hydraulic gradient. Sounds complicated, right? But simply put, it just means how fast water can flow through a material. If your road base has high hydraulic conductivity, heavy stormwater drains away harmlessly into the earth. But if it has low conductivity, that water gets trapped.
This battle against water is a totally universal engineering truth. Even in highly specific documents like the Bhutani Department of Roads Guidelines for Road Drainage Systems, the core principle is exactly the same. Whether you're building a massive interstate highway in the US or a steep mountain pass in the Himalayas, getting water away from the pavement and subgrade as fast as possible is the absolute most fundamental consideration in road design.
So, the crucial point is understanding exactly how this trapped water destroys our roads from the inside out. It's a chain reaction. First, it structurally weakens those unbound granular foundation materials. Then it literally strips the chemical binders right out of the asphalt mixtures. It causes pumping and faulting in concrete, and in colder climates, it's even worse. Trapped water freezes, expands, and creates what's called frost heave, which literally pushes the entire road up from underneath.
All right, moving up from the foundation, let's look at Section 4, Flexible Pavement Systems, Bending, Not Breaking.
How do modern surface layers handle the immense pounding stress of constant heavy traffic? Surprisingly, they do it by bending instead of breaking. Unlike rigid concrete, flexible pavement is actually engineered to slightly deflect or bend when a heavy truck drives over it. I know it sounds a bit counterintuitive. You'd think you want the hardest surface possible, but rigidity isn't always the best defense. By flexing and distributing that heavy load down into those deep base layers we just talked about, the surface actually protects itself from cracking over time.
And there isn't just one single way to build a flexible road either. Engineers have a whole toolkit. Depending on the traffic demands, they might use full-depth asphalt, which skips a separate base layer entirely for quick builds. Or they might use conventional layered structures, a contained rock asphalt mat, or even composite pavements. That last one actually places flexible asphalt right over existing rigid concrete so you get the best of both worlds.
The advantages of these flexible pavements are absolutely massive for keeping our daily commutes running smoothly. First off, the initial material costs are just lower. They're also way easier to install because, unlike rigid concrete, they don't require complex expansion joints. The curation time is super rapid too, often under 24 hours, which means significantly less traffic disruption for all of us. They're less prone to forming dangerous ice glazes, and when damage inevitably does occur, patching or resurfacing is a remarkably simple process.
Now, engineering never stands still, which brings us to our final topic, Section 5, Future Construction Innovations, Building 2026 and Beyond. The entire construction industry is on the brink of a massive high-tech evolution. We are looking at a near future where massive 3D printers extrude concrete structures layer by layer. We'll see robotics and automation on job sites working alongside human crews to tackle labor shortages. Engineers are already using digital twins and metaverse integration to simulate a road's performance long before anyone ever breaks ground. Throw in augmented reality wearables for workers and new green, low-carbon concrete, and we are looking at a totally revolutionized industry.
But for me, perhaps the most exciting leap is advanced sensor networks. Think about this. Soon, our roads will basically become smart devices. By embedding conductive fibers or tiny microsensors directly into the pavement, the road itself will continuously monitor its own temperature, physical load, vibration, and humidity levels. It will essentially be able to predict its own maintenance needs well before a visible problem ever occurs on the surface. How cool is that?
And this brilliantly illustrates the absolute cutting edge of material science. Self-healing concrete embedded with bacteria or microcapsules can autonomously fill cracks, extending the life of structures. We are literally talking about biology integrating with civil engineering. Special bacteria sleep inside the concrete, and the moment a microcrack forms and lets a tiny bit of water in, those bacteria wake up, consume nutrients, and literally produce limestone to patch the crack all by themselves. It is pure sci-fi turned reality. Because of these massive leaps forward, standard statewide engineering guidelines, like the SUDAS Urban Design Manual, are going to have to evolve incredibly fast. The engineering rulebooks of the past simply weren't written to account for AI diagnostics, robotic construction crews, and living, self-healing materials. It's a whole new ballgame. So, I want to leave you with this thought as we wrap up today's explainer. The next time you're driving along and you brace yourself for an impact, consider this. With the rapid integration of smart sensors, perfectly optimized sub-base engineering, and autonomous self-healing biology, will the dreaded pothole soon become nothing more than a relic of the past? It's entirely possible. Keep your eyes on the road ahead because the hidden engineering right under our feet is getting smarter every single day.